right, good morning. Welcome to my stream, and we're going to today, since we finished the roguelike, this was supposed to be roguelike week, but I don't have a roguelike ready after having finished the tutorial, the Rust roguelike tutorial. So the idea here is to switch back to the crafting interpreters thing. And there's two avenues of approach. We have two quests open to us right now. One is to continue with the bytecode interpreter, and the other one is to work on, oh yeah, this I wanted to talk about too. The other one is to work on the fixing the jlox version that we finished a while back. There are error messages that need to be cleaned up and some bugs in here. I was looking at some bugs that this should be, oh, not these ones. There were some, I saw some errors in here that shouldn't be errors. Expected runtime errors. So this is a runtime error, but there are some other things that should succeed that are failing. Like here, missed expected output false on line 7 and so on. So we were supposed to get false, 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 and so on. Falses and trues out of this, and we weren't expecting to see illegal expressions. So there's some bugs somewhere in our jlox port that we need to fix, and it looks like it's mostly in this test. We got 169 tests passing and 70 tests failing. And so it'd be nice to go and clean up a couple of these before we dive into the bytecode thing. And we can just knock them down one at a time. We might be able to get somewhere and finish that up over the course of a few days. This was the other thing I wanted to look at. This is what I found on the NeoVim's GitHub. And right now our config is very sparse. Let's take a look at it. Config and Vim and our init Lua. Right now, this is the way we left it off yesterday. And I tried to add this formatting thing and it didn't work. Although we did have the GD thing. So what I wanted to try doing was putting this in and seeing if this did the trick. Not this part here. This part here, suggested configuration. Else pconfig does not map key bindings or enable completion by default. The following example config provides suggested key maps for most commonly used language server functions and manually trigger completion with omnifunc. So we'll see if we can get completion working and some of these little things working, which would be nice. So let's copy paste. I don't think we need that last loop, I'm guessing, because we have, okay, and then this, is that set anywhere? Okay, so I'm going to leave that alone. And this is what I'll just paste in here. And we'll just see. And then this goes away. This is like this, right? Let's get rid of that one. I think that's the way it was. So I'm just commenting that out. And then we have this thing with the omnifunc, which is the Control X, Control O. And then we have all these key maps. So I wanted to see if this works. This says diagnostic go to prep, diagnostic go to next, so we could try that as well. Let's go into the jlox AST. Take a look at source main, and then try some of these little guys in here and see what they do. So we have GD goes to definition and D goes to declaration. So if I go, I think, well, we had this working before, GD. Yeah, so that went to the definition. If I say G shift D, nothing happens. All right. What if I do try the next one, shift K? All right, it describes it. That's interesting. Shift K. And I can look at read to string maybe, shift K. Oh, okay. So it's giving us some information, which is neat. A little example. How do I make it go away? Escape? No. I guess I just move. Shift K gives us the runtime error. GD goes to definition, and G Shift D should go to declarations, but I guess we don't have that. GI goes to implementation. GI. No? GI. GI. Oh, I see. Oh, I see. It jumps to the impl. If there's an impl for it. So if I go back here, I'm in main now, and I say, okay, I want to look at the implementation of this GI. It jumps to impl. All right. Control K gives signature help. All right. So if I go maybe standard process exit, I can hit Control K. No signature help available. Okay, I'm not sure what that does. Space WA means add workspace folder. I don't want to do that. Remove workspace folder. Print, inspect, workspace folder, WL, space WL. Okay, I guess that's just the workspace folder we're currently in. Space Shift D. Space Shift D is the type definition. Okay. I'm not sure how that differs from definition. RN is rename. Oh, I can rename it. I see. Let's leave it alone. I wonder if it would rename it through the entire workspace. That would be interesting. What else we have? CA for code action. Code action. Generate impl for LOX results. Type number and enter, or click with mouse Q or empty cancels. All right. Interesting. So if I'm on this, I can generate an impl block for it. GR finds references. Oh, very nice. So I can look at all these references. Can I just jump to it by hitting return? Neat. Let me try this one here. Yeah, look at that. Okay. And then space F does formatting, which will be nice because let's see if I do this and do this and do this. Right, just shift it off like that and then just hit space F. Yeah, it jumps it back. Okay, let's undo all that. Okay, so I think we just need to have a cheat sheet here. Let me just undo all my changes. How many things did I change? Oh, I changed every. Oh, because it did rename LOX result. I wonder if there was a way to to cancel out of that without having to go through all this. Okay, so it did actually go through every file where LOX result was and rename it. That's neat. All right, so this is good. I'm going to use this as my little cheat sheet here. But meanwhile, let's see if we can fix this first mistake. Unexpected character. So we were supposed to see error at B, expect close paren after arguments. And all we did was put in unexpected character. So let's see if we can find that. So that's in self-scanner. And here it is. So this should be an error at B, expect something. So let's take a look at our error thing and see how we print that out. Okay, so it should be a parse error. And we didn't make a parse error, we made a regular error. So if I change this to a parse error, where is parse error? And it takes a token. Do we have a token at this point? Maybe we don't have a token. Maybe that's the problem. Right, because a regular error just takes a line number and doesn't take anything else. Here we have token, runtime error is a token. Token, we can generate a token from isMatch. or a token type is match, but that's what we're doing. All we have is a character. So maybe we should create a scan error, which generates this thing here. Because this is what we want. So this is what we want, this parse error, but without the token. We have token line, token as string. I guess we could generate a token here. What would that take to generate a token? Let's take a look at our token code. Token new. We have the token type, the string, and the a literal option, which I guess we're ignoring, because I think the token as string just uses lexeme, and then the line number. Oh, so what's the token type? I guess we don't care what the token type is. So we'd have to pick one. I guess we could just use string. So here, all I'm thinking is we just say token new, token type string. I should go back here so I can see what this function signature is. Oh, there's the help now. What's the help for this function signature? Or I could use the omnifunc. Can I? Shift K. There it is. Okay. So token type string. Oh, now it's gone. This is the lexeme. So I think we could just say, oops, what is it? It's C. To string, can I do that? Nope. And then I have to look here. Option object. Okay, none. And the line number is self line. Right, and then we can delete that. Oh no, we have that on error. Okay. Oh, let's try formatting. Space F. Yep, that works. Okay, and then we'll do a check. I can't create token. Oh, I can create token. I just need to ampersand. All right. So now we need to build it, right? Or we'll build release and see if that fixes this. Okay, I have error at pipe, unexpected character. Missing expected. Oh, I see. I see. We're supposed to see this and then this. We're supposed to see both errors. Oh, let me take a look at this test here. Oh, this is probably under the Dart thing, right? No, it's there. Okay. 14. Yeah, so we're supposed to see two lines here. Error at B, expect close bracket after arguments. Really? Why? Yeah, it should be complaining about the pipe. Okay, that's weird. Because the pipe character is the one that's confusing. Oh, maybe we're supposed to look at the next token. Oh, unexpected character. So we're supposed to see this line here, line 3, something. And if I run this with this, what's our error? Berduda, hi. So we're seeing this, error at blah, and then this saying expect close print after character. This is the unexpected character. I think what's supposed to happen is we're supposed to just blow through it. Instead of returning an error, we're supposed to report the error and just keep going. And instead of all of this thing that I just did, self line, we're supposed to just report the unexpected character like this. but not return it. Just keep going. Do we have a function error? No, we don't. Okay. So if we do that, oh, now the match doesn't return something. So maybe we need to return that okay here. Because the match has to be equal. Oh. Yeah, because each one of these needs to return the same thing. These and all prior arms are found to be of type nothing. Oh, okay, so we can just do that. Can we do that? I think so. Yeah, okay. So now if I run this, first I have to build it. Now if I run it, what kind of error do we get? Okay, so now we see unexpected character on line 3 and error at B. Okay, so now maybe the Dart test will pass. Nope. Oh, because I left off a full stop here, period at the end. Okay. Now maybe it'll pass. Nice. Okay. So what's the next one? This is the next error. So let's fix this one, and then we'll switch over to the bytecode thing. Okay. So we have grouping. Expected return code 65. It got 0. Standard error. Error at equals. Invalid assignment target. Okay. So again, what we'll do is we'll test. Oh, I forgot to copy the test. Test. There we go. So now what we'll do is we'll run it here. So this is what I'm printing out, and then what is the test runner expecting? It's expecting error at equals invalid assignment target. Okay, that's what we did. Oh, and then we're supposed to return a 65 echo question mark. And we're returning 0. Okay, so if we look at our invalid assignment target, we report this error, and then what this should do is set had error to true, right? So now in our parser, when we check the parse result, if parser here we go, parser success. So so instead of doing parser success, we should have the parser. We have parser parse right here. It should throw the error directly. Right, we can say if had self had error, then return error. Oh, we don't want to call parse error or anything like that, because that'll also print an error. So do we just construct a new jlox result? I just want to create an error without reporting it, because we've already reported an error. And I want this guy here in main to blow up if we had an error. So we don't have a non-reporting error. So we can just create a fail case here. And pub fun fail. Jlox result. Jlox result. Fail. and it doesn't report anything. We can just say lox result fail. Right? Else, okay statements. Right? Will that check? It doesn't. Oh, because we need to check on report. And we should never see this. Oh, why is that there? I guess it doesn't matter. Lox result fail. And that's just going to be panic should not get here. We shouldn't ever report that. Okay. There we go. So let's build that and see if that results in us reporting a 65. Good. So that also means we can clean up the other thing. But first, let's just run this Dart test and see if we get past that one. I forgot which one it was. Yep. Okay. So now we're up to 70. We're 176 tests passed and 63 failing. So we're getting better. And then we have to fix this one. Okay. But that'll be for tomorrow. So the other thing, before I forget, is to go through here, and now partial success shouldn't ever be used, because if we fail, we're just going to return from this question mark here. So we can just get rid of this like that. Right, like that, and that'll be done. And then we'll do the same thing for the resolver when we fix that. It also means that in parser we don't need success. Nope, that's all the. So that should check. Cargo clippy. Huh. Okay, we have a few things to fix here. Okay, let's fix this. It says remove the final this, but I thought, okay. 128. You know what I can do is, let me do it over here. CD, documents, dev, lox, AST, cargo, watch, jlox, clippy. Yeah. Okay, so let's fix it from the bottom to the top. Interpreter. What is it complaining about here? Sum with OK is redundant. Okay. 171. But now it fails. Sum with OK is redundant, but it needs it. Expected enum result. So if I put that back, oh, if let OK, duh, okay. If let OK, there. There we go. Okay, so then this replaces binding with the actual thing. All right. If let object class superclass. Oh, I see. So we don't need to do the double if let. I got it. Object class. Right? That's what they're saying? Oh no, okay, object class superclass. Object class superclass. And then we can just do that, else this. I'm missing this. There we go. Nice. Okay, and then we have this one last one here in the scanner, which is the one I just added to make the compiler not complaining. Oh yeah, we don't need to do that. Okay. Good. All right, so all cleaned up. Git status. Git add source. Git commit. sham clippy and error fixing. Reporting. Error reporting. Fixing. Okay. So we're getting better. Only 63 tests failing. That's good. So we've done that. And now it's time to go back to our bytecode interpreter. Okay, so the first thing I wanted to talk about was that Zeta numbers gave us a quick little fix. Let's take a look. Get status. Oh, get show this. What I was trying to do was just name the function, but we can do it with a closure. And that's what Zeta numbers submitted the PR for. Just throwing the closure in there. That was the thing we were stumbling over a couple of weeks back. Compiler, right here. Just if I take this out and then just put in compiler grouping, it was giving us an error. One type is more general than the other, and I think the reason was that I was forgetting that compiler took a tick A here. And so we needed to make a tick A for here. And I think maybe, you know what, maybe we can just throw it here. Yeah, okay, so that fixes the problem also, right? So we can actually do compiler grouping. Oops. We can do it this way by passing in a to make sure that the lifetimes match, right? And I think that was the problem, was the lifetimes weren't matching between parse rule and the compiler, and now they are by forcing them to be the same. Or we could just use it with a closure. And since we were given this PR, we'll stick with this. The other thing I wanted to do was, right now the way this is working is every time we call get rule, it generates a new parse rule, right? So the default parse rule has these, and all of these are this. It would be nice to do this, something similar to the way this table works, is it's all done ahead of time. This is actually done in C at compile time, right? So the compiler sets this table up, and then all you do is do a lookup based on the rule. Based on the token, right? So each token has its own rule. You look up the rule based on the token index, and you get the tuple, which contains the prefix, the infix functions, and then the precedence for that rule, for that token. To do that in Rust, we either have to use a lazy static to set it up, but I don't want to do lazy statics only because I'm trying to make this crate free. Right? If we look at our cargo toml, there are no dependencies. So we want to make this just clean Rust without any dependencies, which means we don't use lazy static. So I think the only other option would be, when we create the compiler, is to generate the table here as part of the compiler, and then do the lookups based on the tokens. Do I have the tokens? Oh, right, I can use GD. So these tokens are the ones that we use to do the lookup. If I set the first one to 0, then, oh, that's interesting, there's no undefined here. Then all of these should be able to be converted into usizes. Right? I should be able to say token type as usize and look it up in a table. So here's what I'm thinking, is we create a vector in our compiler. Where's our compiler? Here it is. called rules, and we'll make it a vec of type parse rule. Right, and then down in here, we'll just say rules. And then we'll set up the rules here when we generate the new compiler. But that means every time we have a chunk to compile, we're going to generate this table, which isn't great, but it's better than creating a new rule each time we need to look up a rule. So it's one step in the right direction. And maybe lazy static would be a better option in terms of performance. But until we see performance issues, let's not try to pre-optimize. So we're going to say let mut rules is vec bang of, and then we're going to create a parse rule of the default, and we're going to use token type undefined. What's the last one? Can we do this? Yeah, undefined was the last one, which we're not going to use. Actually, number of tokens. Let's do it that way. And that way we could just set them all up that way. And then so let's say here, let's go over here, and then for our parse rule, let's just grab this as the default, right? Now, will this compile? Of course not. The trait bound parse rule clone is not. Oh. Okay. Do that? I can. Look at that. So these options can be cloned, the precedents can be cloned. That's good. Good. Okay. So now what we have are the rules, and we can just insert in here each rule, right? So we could just say, why did that tab over like that? We can say rules of, and all we have to do is set the different ones, right? So we have rules of token type left paren as usize is equal to parse rule of, and we just have it right here, right? And that should work, and it does. And that way down here in get rule, all we have to do is say return self dot rules of t type as usize. And that goes away. Yes. Okay. So now all we have to do is put in all the rules, all the special rules. So we have the minus. Let's just copy this. Minus. And it's going to take a unary, a binary, and a prec term. Do we have unary? Yeah, we do. Okay. I forgot which ones we actually did. So this will be unary. This will be some C and C dot binary. And then precedence is going to be term. Okay, and then the next one is going to be plus, which does not have a prefix, so that's a none. And then it's got a binary and prec term. Slash and star also have that same so we can do that, slash and star. And the next one is number. Which takes a sum C number, and none for the infix, And then the rest. Oh, and this is prec none. Oh, oops, and slash star have prec factor. Right? What else did I miss? Plus and minus both prec term, right? None, factor, a whole bunch of nuns. Yeah, everything else is none. So there's very few precedences. We have a whole bunch of precedences, right? But from the table, we only start with a few. We have, yeah. So that's none. I'm just double checking because you mess this up and that's where everything explodes. Prec none. Okay. So I think that's everything. And now we can look up. So we have all the rules set this way, and then we can look them up using the get rule function, which is, I guess we didn't do that. Okay. I forget what I read last time, so I'm just going to reread starting from Pratt parser here. We now have all the pieces and parts of the compiler laid out. We have a function for each grammar production, number, grouping, unary, and binary. We still need to implement parse precedence and get rule. We do have get rule. We just haven't implemented parse precedence yet. Okay. We also know that we need a table that, given a token type, lets us find the function to compile prefix expression, function to compile infix expression, and a precedence of an infix expression. Yeah, I remember reading that. So this is what our parse rule looks like as our parse function, and this is the table that we just worked on. See what I mean about not wanting to revisit a table each time we needed a new column? It's a beast. If you haven't seen the token dot syntax in C-array literal, it's C99's designated initializer syntax. All right, so C99 is what, 23 years old now? We should be aware of it. You can see how the grouping and unary are slotted into the prefix parser column. Right, there's grouping and unary, and also number in the prefix parser. The next column, binary, is wired up to the 4 arithmetic instructions, right? And there are 1, 2, 3, and 4. Those infix operators also have their precedences set in the last column. Term, term, factor, factor. Term, term, factor, factor. Perfect. Aside from those, the rest of the table is full of null and prec none. Most of those empty cells are because there's no expression associated with those tokens. You can't start an expression with, say, else, and close squiggly bracket. Oh, and close brace would make for a pretty confusing infix operator, yes. But also we haven't filled in the entire grammar yet. In later chapters, as we add new expression types, some of these slots will get functions in them. Aha. One of the things I like about this approach to parsing is that it makes it very easy to see which tokens are in use by the grammar and which are available. Well, sort of. I didn't do it that way. Now that we have the table, we're finally ready to write the code that uses it. That's where our Pratt parser comes to life. The easiest function to define is getRule, so we did that one already. It simply returns the rule at the given index. It's called by binary to look up the precedence of the current operator. Oh, you know what? Oh, getRule passes back a parse rule instead of a reference to a parse rule, right? Which means it's going to be cloning it each time. There we go. Okay, that's better. I don't want it to clone. It's called by binary to look up the precedence of the current operator, right? GI, right? Gives us the... Oh, I guess not. What was... Yeah, I thought it was GI. To get the implementations. Oh, that... Yeah. Okay. References is GR. Sorry. GR. Right. So this here is where it's used. In binary. Okay. Binary is defined before the rules table so the table can store a pointer to it. Okay, we don't need to worry about that in Rust. That means the body of binary cannot access the table directly. Oh, so the only reason we call getRule is to look it up in the thing, but we don't need to do that then. in Rust. We can just access the rules directly. We can just say self rules. Operator type. And we don't need get rule. Oh, as use as. Yeah. Okay. So we don't have to do all that fancy schmancy stuff in Rust because we already have access to everything. Instead, we wrap the lookup in a function. Okay, that lets us forward declare get rule before the definition of binary and then define get rule after the table. We'll need a couple of other forward declarations to handle the fact that our grammar is recursive, so let's get them out of the way. Again, we don't need to worry about this. This is what happens when you write your VM in a language that was designed to be compiled on a PDP-11. Yes. Yeah, C is single pass, so you have to everything has to be defined before you get to it, whereas Rust, you can mix and match everything. If you're following along and implementing jlox yourself, pay close attention to the little annotations that tell you where to put those code snippets. Don't worry though, if you get it wrong, the C compiler will be happy to tell you. Those add after end compiler. Oh, interesting. So the way I do my forward declarations when I'm writing C is I put them at the top of the file. Here he's just putting them just before they're actually used. I guess that's personal style. I just like having everything grouped together rather than sprinkling them through the file. Now we're getting to the fun stuff. The maestro that orchestrates all of the parsing functions we've defined is parse precedence. Let's start with parsing prefix instructions. All right, so here we finally get to parse precedence, which is right here. All right. So we're going to call advance first, self-advance. And then we're going to grep and get the rule. Oh, see, we are calling get rule here. And grabbing the prefix function. Let prefix rule equal self rules of parser. Oh, parser previous types. It's self parser previous t type as usize dot prefix. If prefix rule is null, error expect expression. Okay, so we're going to say if let sum prefix rule then we're going to call prefix rule. Ooh. Do we have to pass in self? How's that going to work? How do I call that? Because this is now the closure, right? Can I just do that? Or is that going to blow up? Else, self error, expect expression. Is that going to even work? Let's see. Yeah. Oh, expected one argument. What's the argument? Oh, it does pass in the compiler. Okay, yeah. Oops, I didn't mean to do that. Prefix rule. So we do pass in self. But it has to be mutable. Okay. We read the next token and look up the corresponding parse rule. If there is no prefix parser, then the token must be a syntax error. We report that and return to the caller. Otherwise, we call that prefix parse function and let it do its thing. That prefix parser compiles the rest of the prefix expression, consuming any other tokens it needs, and returns back here. Infix expressions are where it gets interesting since precedence comes into play. The implementation is remarkably simple. Alright, so we've called prefix rule and then we say while precedence is less than self precedence. Really? Where's precedence coming from? Oh, it's passed in. It's passed in. I missed that. Okay. Duh. Is less than the precedence of the rule, self, rules, self, parser, current, t-type, as usize, dot precedence. Then we call self advance. And then we get the infix rule, the same way we did the other one. Oh, and we just call it blindly. We don't even look to see if it's not an option. If let some infix rule equals self parser previous type as usize dot infix, then infix rule self. Is that going to complain about? No, it didn't. Wow. That just worked. That's the whole thing, really. Here's how the entire function works. At the beginning of parse precedence, we look up the prefix parser for the current token. The first token is always going to belong to some kind of prefix expression by definition. It may turn out to be nested as an operand inside one or more infix expressions, but as you read the code from left to right, the first token you hit always belongs to a prefix expression. Right, inside the prefix, there's only three of them. There's a grouping one, which is open paren. There's a negative sign, for minus, or it's a number. You can't start with anything else. You can't start an expression with equal sign, for example. So it's always going to be one of these three. After parsing that, which may consume more tokens, the prefix expression is done. Now we look for an infix parser for the next token. If we find one, it means the prefix expression we already compiled might be an operand for it, but only if the call to parse precedence has a precedence that is low enough to permit that infix operator. If the next token is too low precedence, or isn't an infix operator at all, we're done. We've parsed as much expression as we can. Otherwise, we consume the operator and hand off control to the infix parser we found. It consumes whatever other tokens it needs, usually the right operand, and returns back to parse precedence. Then we loop back around and see if the next token is also a valid infix operator that can take the entire preceding expression as its operand. We keep looping like that, crunching through infix operators and their operands until we hit a token that isn't an infix operator or is too low precedence and stop. That's a lot of prose. But if you really want to mind meld with Von Pratt and fully understand the algorithm, step through the parser in your debugger as it works through some expressions. Maybe a picture will help. Is it even possible at this point to run this and have it parse expressions? We have 8 warnings because we're not actually doing Can it bar self is mutable because it's already barred as immutable? Unused import chunk. Okay, well I can fix the chunk thing. Oh, that's right. We had chunk there because of we were generating a chunk on the fly. But in compiler now, it's telling us it can't borrow this. This borrowing pattern is not meant to be accepted and may become a hard error in the future. So if we look at this line 208 here, so we're borrowing in immutably here, and then here we're mutating it. Oh. So I think, do we use rule anywhere else in here? We don't. So I could just call precedence next here, right? And then just pass that in here. Okay, and does that fix that? It does. Okay, and then we just have functions that are not used. Right? Never used, never used, never used, never used. Okay, which I'm not worried about. I'm not worried about those because we'll get to those eventually. All right, so that fixes that one. That was easy enough to do. Hopefully this doesn't clone the parse rule. Right? Can we run this? Does this do anything if I say 4 plus 5? Error at 4, expect end of expression. Okay, so something that's not where I don't think it's wired up, right? Let's take a look. Here's where we do this. We do this VM interpret the line. So if I go to interpret, it calls a compiler, tries to compile the source, right? So if I go to compile, oh, we're not calling expression yet. I commented that out. If I uncomment that, it fails because question mark can't be applied to that. Okay. All right, let's see if this runs. Oh, look at that. Four and 5 add 9, so that works. Whoa! Did this just all work? 4 divided by 5, 0.8. 4 times 5, 20. 4 plus 5 times 6, 54. 4 plus 5 times 6 is 54. Okay, so it's not quite working, right? Because this is 9 times 6, which is 54, and this should be 6 times 5, which is 30, plus 4, which is 34. And so we're getting 54. So something's not working. We have to debug this, right, before we can go any further, because this is like the heart of our expression calculator. Let's see, what did I do wrong? Source compiler. Expression. Yeah, so this just calls parse precedence. And parse precedence is the thing that's failing here. Well, precedence is less than self-rule. So it might be this, partial ORed thing. If term is less than factor. Did I get it backwards? Oh, less than or equal to. Let's see if that was the problem. Cargo run. 4 plus 5 times 6. 34. Okay, that was the bug. Problem fixed. All right. So we did this, So that was 17.6, right? And that was called a Pratt parser. Cargo clippy. Ooh. Oh, well, okay. I'm not worried about the associated functions never used. What is this, though? Writing a string instead of stir involves a new object where a slice will do. Okay, let's try changing that. Will that compile? It won't. Expected string found stir. Right, which isn't surprising. Can I do a stir here? Yeah, I can. Okay, and then, oops, I didn't want to check. I wanted to do a cargo clippy. And interpret, the same thing. So let's see if we can do that in the VM. And okay, so that works. So cargo clippy. Yep, so this is all just associated functions. Okay, so data, git add source, git commit -m, section 17.6. Oops. Pratt parser. Done. All right. We did that. Dumping chunks. Okay. Should have been called blowing chunks, right? While we're here in the core of our compiler, we should put in some instrumentation. To help debug the generated bytecode, we'll add support for dumping the chunk once the compiler finishes. We had some temporary logging earlier when we hand authored the chunk. Now we'll put in some real code so that we can enable it whenever we want. All right, so we already have the trace execution thing. All right, we're tracing the execution of the code here. But now we're going to have this new flag called print code. So I'm going to make it another feature. Default is going to be called debug print code. And I think I can just do it like this, debug print code. Right? To enable it. And there was a features, no default features, right? We can run it like this and just say 4 plus 5 times 6, and it just prints it out without any feature, any stuff. So we can run it either way. Pump. Okay, so now here's where we're going to call disassemble. We're going to, do the debug print code thing here. Okay. And so where is end compiler? It's right there. Emit return. And then after that, we're going to check the features. CFG. Oops. Here it is. This is the format I'm looking for here. This is debug print code. If parser didn't have an error. What's this parser? Oh, that's the thing inside here. Okay, never mind. Let's pull up the compiler, and it's up here. Do we have it? We do have it had error. Okay. If self parser had error, borrow. I think I have to do it like that, right? Then we're going to say disassemble chunk. Self dot chunk. Disassemble code. I think. Does it take a string? It takes a 2-stringable thing. Okay. So let's see if this all works. Yeah, we're down to 5 warnings now. We do this only if the code was free of errors. After a syntax error, the compiler keeps on going, but it's in kind of a weird state and might produce broken code. That's harmless because it won't get executed, but we'll just confuse ourselves if we try to read it. Finally, to access disassemble chunk. Yeah. Okay, we don't need to worry about that. So if I say cargo run, I say 4 plus 5 times 6. It now dumps out on line. It says line 1 has these instructions, and then here's the execution. Neat. We made it. This was the last major section to install in our VM's compilation and execution pipeline. Our interpreter doesn't look like much, but inside it is scanning, parsing, compiling to bytecode, and executing. Fire up the VM and type in an expression. If we did everything right, it should calculate and print the result. We now have a very over-engineered arithmetic calculator. We have a lot of language features to add in the coming chapters, but the foundation is in place. To really understand the parser, you need to see how execution threads through the interesting parsing functions and the parser functions stored in the table. Take this strange expression. We should be able to parse that, right? Look at that. Write a trace of how those functions are called, show the order they are called, which calls which, and the arguments passed to them. So it's negating a 1, it's adding a 2, it's multiplying by 3, and then it's negating the 4 and then subtracting minus 4 from 3, which comes up to 7, which is correct. All right, so that worked. The parse rule row for token minus has both prefix and infix function pointers. That's because minus sign is both a prefix operator, unary negation, and an infix one, subtraction. In the full LOX language, what other tokens can be used in both prefix and infix positions? What about in C or in another language of your choice? Well, I think the other one in LOX is bang, right? Can be used in prefix. Oh, no. It's used as prefix, but not as infix. I don't remember. I guess plus should be able to. Yeah. I don't know. I can't think of it off the top of my head here. You might be wondering about complex mixed-fix expressions that have more than two operands separated by tokens. C's conditional or ternary operator, question mark, colon, is a widely known one. Add support for that operator to the compiler. You don't have to generate any bytecode, just show how you would hook it up to the parser and handle the operands. Design note. Oh, I'm not going to do that. Design note. It's just parsing. I'm going to make a claim here that will be unpopular with some compiler and language people. It's okay if you don't agree. Personally, I learn more from strongly stated opinions that I disagree with than I do from several pages of qualifiers and equivocation. My claim is that parsing doesn't matter. Okay. Over the years, many programming language people, especially in academia, have gotten really into parsers and taking them very seriously. Initially, it was the compiler folks who got into compilers, LALR, and stuff like that. The first half of the Dragon book is a long love letter to the wonders of parser generators. Later, the functional programming folks got into parser combinators, packrat parsers, and other sorts of things. Because obviously, if you give a functional programmer a problem, the first thing they do is whip out a pocket full of higher order functions. Over in math and algorithm analysis land, there's a long legacy of research into proving time and memory usage for various parsing techniques, transforming parsing problems into other problems and back, and assigning complexity cases to different grammars. Whoa, I'm starting to get lost here. All of us suffer from the vice of when all you have is a hammer, everything looks like a nail, but perhaps none so visibly as compiler people. You wouldn't believe the breadth of software problems that miraculously seem to require a new little language in their solution as soon as you ask a compiler hacker for help. Yak and other compilers are the most delightfully recursive example. Wow, writing compilers is a chore. I know, let's write a compiler to write our compiler for us. For the record, I don't claim immunity to this affliction. There is, Rust has a, Rust, what's it called, Pear, Peach, something like that, Rust. Compiler. Great. There's a Rust package compiler generator. Whoa. My hands were a little bit cancel. Generator crate. Peg, LRPAR, parser tooling. No, none of these ring a bell. Clap is command line parsing. Pest, that was it. Pest. I knew it began with a P. What was I saying before? Pear or peach or something like that? Okay, pest. It's a general purpose parser written in Rust with a focus on accessibility, correctness, and performance. So one of the things that would be nice in order to try out pest is to write a LOX compiler using pest. It just uses the standard, or very similar to BNF, right, to generate the parser. I've never played with it, but according to Pest's own page, Pest is better than Namasurdi. Okay. Where was I? All right, so we finished this chapter. We're all done. What changes did we make? Not much. All we did was add Clippy should be happy. All we did was add a little thing to it to disassemble chunks. Git add cargo toml and source git commit -m dumping section 17.7 dumping chunks. Very small section, very little change, but it's there. And we still don't have, we're not calling free. And write opcode is never used. But it's got to be used, right? How are we putting these opcodes in here? Let's just take a quick look. Write opcode. And then in our compiler, chunk dot. So emit byte. Oh, I see. I'm calling emit byte into. So it just requires chunk write. So we actually don't need write opcode anymore. Right? Because I'm converting the opcode into a byte using this thing. So I don't have to worry about this. Boom, boom, boom. Gone. All right. And the other one was free. We're never calling free. And it's all the frees, right? Chunk free is not called, compiler free, and value free is never called. This one I get because all we're doing is creating constants, but we're never cleaning them up. And I think when we get to garbage collection, that's when we're going to use that guy. So, and we never use previous on the compiler, and chunk is never freed. Do we, in our compiler, do we call free? We don't have a free here. In our VM, do we have a free? We do. Oh, so maybe, yeah, self-run chunk. Maybe after self-run chunk, we should say let result equals self-run chunk, and then we can chunk dot free. I mean, we don't really need this because Rust is going to clean it up for us anyway. Oh, and I forgot to return the result. Duh. All right, so that's down to 2 warnings. Just is that we're not using previous. Okay, so let's get rid of previous. Not that previous. This previous. We don't need this. We may in the future. I don't know. So I'll just leave that there. All right, git status, git add source, git commit -m clippy cleanup. Done. Okay, so that's that. Let's look on types of values. How much time do I have? Oh, I got time. Okay. The past few chapters were huge, packed full of complex techniques and pages of code. In this chapter, there's only one new concept to learn, and a scattering of straightforward code. You've earned a respite. jlox is dynamically typed. A single variable can hold a boolean, number, or string at different points in time. At least that's the idea. Right now in jlox, all values are numbers. By the end of the chapter, it will also support booleans and nil. While those aren't super interesting, they force us to figure out how our value representation can dynamically handle different types. There's a third category next to statically typed and dynamically typed, unityped. In that paradigm, all variables have a single type, usually a machine register integer. Unityped languages aren't common today, but some Forths and BCPL, the language that inspired C, worked like this. As of this moment, jlox is unityped. But we're going to change that. All right, tagged unions. The nice thing about working in C is that we can build our data structures from the raw bits up. The bad thing is that we have to do that. C doesn't give you much for free at compile time and even less at runtime. As far as C is concerned, the universe is an undifferentiated array of bytes. It's up to us to decide how many of those bytes to use and what they mean. Yeah, hence the source of a million different security issues, right? In order to choose a value representation, we need to answer 2 key questions. How do we represent the type of a value? If you try to, say, multiply a number by true, we need to detect that error at runtime and report it. In order to do that, we need to be able to tell what type of values type, we need to be able to tell what a value's type is. How do we store the value itself? We need to not only be able to tell that there is a number, that 3 is a number, but that it's different from the number 4. I know it seems obvious, right? But we're operating at a level where it's good to spell these things out. Since we're not just designing this language but building it ourselves, when answering these two questions, we also have to keep in mind the implementer's eternal quest to do it efficiently. Language hackers over the years have come up with a variety of clever ways to pack the above information into as few bits as possible. For now, we'll start with the simplest classic solution, a tagged union. Value contains two parts, a type tag and a payload for the actual value. All right, so this is, I'm just going to take a break here because I think where this is going is, if I look at value, right now value is just F64. But I think what this is going to end up being, right, because we're going to say bool, nil, or number. So we could define this struct as an 8-byte double followed by a 1-byte bool. That's a waste of memory. A value can't be simultaneously both a number and a boolean. So you can have them overlap. In the C, you make them a union, right? So you have a value type. In Rust, of course, you can make this different. You can say pub struct value and say boolean. Bool. Or number F64. And if I do this, it's going to blow everything up because we're assuming that everything's F64. So this is gonna kill our universe here. All right, so we have the type, which is this thing, some padding, and then the number. And the reason for the padding on a 64-bit machine is because double is a 64-bit number and you have to store on a 64-bit boundary. And value type is an enum, and enums are 32 bits. So there's the 32 bits, there's the wasted bytes, the hole in the struct, so to speak, and then you actually have the value, which boolean a number, and then if we put string, we'll have a pointer to a string here, or whatever. The 4-byte tag comes first, and then union. Most architectures prefer the values to be aligned to their size, right? Values are 16 bytes, which seems a little large. We'll improve it later. Okay, interesting. In the meantime, they're still small enough to store on the C stack and pass around by value. jlox's semantics allow that because the only types we support so far are immutable. If we pass a copy of the value containing the number 3 to some function, we don't need to worry about the caller seeing modifications to the value. You can't modify 3. It's 3 forever. We can move the tag field after the union, but that doesn't help much either. Whenever we create an array of values, which is where most of our memory usage for values will be, the C compiler will insert that same padding between each value to keep the doubles aligned, right? And this is how to get the values out. Oh, we need nil. Okay, so let's see what blows up. If I try to compile this, everything's gonna blow up. Oops. Oh, pub enum. My mistake. Yeah, so now we can't just parse the number into a value. It actually has to be a. Oh, can we do this? No, you can't do that, right? That's not a type. All right, so we'll have to think about how we're going to change this parsing. We can parse it into an F64 and then create a new value, number, value. And now we can't display it because we can't, how do we print out this thing? Right, so a lot of this is going to be useless to us, right? This is how to extract Boolean values and how to, how to assign Boolean values, right? And how to extract them. which is something that we'll just do. I guess we can impl display, right? Impl display value. And what's it going to tell us? What do we have to do? Oh, not found in the scope. We have to import standard format display. Is that something that we have a thing for? We don't. That would be nice to have something where we can have it automatically pull in the use statement. Is that something that LSP supports? I'll have to look that up. So if we do that, now it's going to tell us we didn't implement missing format. Yeah. So let's put that there. And do that. And that should clean that up. Oh, formatter. Formatter comes from standard format formatter. Okay. It doesn't do anything right now, but that's all right. And now we can't negate a value. All right, so that's something we'll have to also do. We also can't add them. Where's add? Yeah, there's add, subtract, multiply, and divide. And what we did last time for our AST was I just implemented those operators. But then we ran into problems because what if the values, what's nil plus 12, right? We had to be able to throw errors, and we couldn't throw errors. So I think what we need to do is change this. Let's change these to F64s, right? Oh. This has to be valid for all binary operations, right? So somewhere in here is where we're going to actually have to do the work of checking to see if the values are correct to use. Right? Meanwhile, we could implement oops. Yeah, there we go. We can implement this standard ops. Should I just do this add sub all div neg? Right? And then we can implement those. Self other value. Is that the way it works? And then returns value. And then we're gonna match self other, and that'll be a value number A. Oops. And value number B, and return value number A plus B. And then all the other ones will panic. Invalid operation. This is just for now, just to get it to compile. I think, oh, output, type output is value. Oh, I guess we just pass value by value. All right, so that worked. So then we can do the same thing for instead of add, we'll do subtract. Change that to a minus, mul, and do a multiplication, and then div, and do division, and then we need to, oops, we need to do negation, impl neg value, output, and I might have to undo all of this anyway when we add the binary stuff. Self value match self value number a value number negative a panic. All right. Oops. VALUE. And we still have this. Move occurs because value has value, which is not moved when copy. Wait, this is an enum. You can't derive copy for enum, right? Right, enums can't. Oh, the enums can do that. Okay, and what are the errors? Boolean is not used and nil is not used. Okay. All right, so this still compiles. I should still be able to say 4 plus 5 times 6, and it blows up. Not yet implemented. Oh, I'm trying to put in the constant as a value, but it's not there. So let's take a look at that. What was the line number? Line 13. Oh, I didn't put the display in there. Okay, done. Match. Self. Value. Boolean. And then this just becomes. Oh, this needs the formatter name. Right bang. F. B. That's easy enough. And then we'll do the same thing for number and nil. Right? And then nil just becomes nil. Okay. 4 plus 5 times 6. There we go. 34. Okay, so that all still works. So we've converted this over to this, to using Rust enums. It's still kind of messy, but I'll still call this section. Clippy. Yeah, so it's just those. Section 18.2. What was it called? Lots values and C values. Okay. Dynamically typed numbers. We got a value representation and the tools to convert to and from it. Okay, sort of. All that's left is to get jlox running again, is to grind through the code and fix every place where data moves across that boundary. This is one of those sections of the book that isn't exactly mind-blowing, but I promised I'd show you every single line of code, so here we are. Val macros lift the C value into heavens, as macros bring it back down. Oh, I see, they're doing that. Yeah. So we have this. This is all working. Right, I did this part, I did this part. And so now unary negation and runtime errors. This is where we get interesting. The next simplest operation is unary negation. It pops a value off the stack, negates it, and pushes the result. Now that we have other types of values, we can't assume the operand is a number anymore. User could just as well do print negative false. We need to handle that gracefully, which means it's time for runtime errors. Before performing an operation that requires a certain type, we need to make sure the value is that type. All right, so this is where we get into... is it in our VM that we do this? Yeah. So here in the VM, we have opcode negate. Once we pop the value off the stack, we have to see, is this value negatable? And we can check that by saying let value number, if let value number, value is this, then we can do that. Oh, no, we can't. Because we actually want the value number so we can negate it. We could just generate it, but then... Yeah, and then we take away the negation thing. Value number this. All right, that's the easy one. Else, we're going to create this runtime error, which we don't have yet. Yep, okay, so we're going to have runtime error here. Self runtime error, format, bang. And I'm doing it this way because I can see this, he's doing a var args thing. So let's just take a string. That's easy enough to just do inline here, right? Oh, you don't even have to do that. Operand must be a number. And then return interpret runtime error. So return error, interpret result, runtime error. Okay, and that we do this, and we don't actually need the negative thing, right? And then fn runtime error. You know, this can just do it, right? It's going to call reset stack, which doesn't exist. Oh, I see. We're going to do a peek first. I missed that part. For unary negation, it looks like this. We're going to say if the top number is if the top value is not a number, then do that. Otherwise, we're going to do the thing. Okay, so if it's a pop, we're going to say last. Is that, I guess we can do this, right? And then we can say let value equal self stack pop unwrap. And we can do this and still use the negation thing. Otherwise, we leave the stack alone, right? Okay, and then runtime error here. We can have this return. How do we return error? Because I want to say something like this. Say return this, and that's the result. I guess that's one way to do it. So what this is going to do is going to take the string. Here it's just called format, but this is just error string t to string. Right, and then size t instruction is this. So we're going to get the instruction number, which is just IP in our version, -1. It gets the line of that instruction and then prints that out. Okay, so we can do that by saying self IP -1 is the instruction. So we can say that line is equal to self chunk self chunk doesn't exist. All right, we're passing chunk around. That's unfortunate. I'm sure there's a better way to do it. So then we say self chunk self IP -1 dot what? Chunk. Let's take a look at chunk to see where we get the line from. Oh yeah, it's just the same thing. So chunk lines, but it's not pub. Is there a way I can get the line from the instruction? Yeah, so we can just say get line. For that value. And I can just add that here. Pub fun get line, self IP, usize, self, oh, what is line? Line is an array of, it is usize, okay. Line IP. All right, so then we have that line, and then we can just say println line in script. Oh, we have this fputS first. Okay, so before we do that, println error string to string. Let's call error message. A string, right? And then this in script, and we have the line there. That's that, and then we're going to call reset stack, self reset stack, and then we're going to turn an error of interpret result runtime error, and that's that. Oh, lines. Pop is a function, and this is something wrong. This doesn't have a size known at compile time. And here's reset stack, which we don't have yet. Okay. What's the other error? A runtime error? No, runtime error. Okay, there we go. Very good. So yeah, so this is all we're doing is adding this error stuff here. First we check to see if the value on top. Oh, thank you, Locksort. Thank you for the follow. Sorry, I don't know how to pronounce your name. I was just trying to scan it again with my eyes and it wasn't working. So if it's not a number, then we report the runtime error. Otherwise, we keep going. And only after this validation do we unwrap the operand, negate it, and wrap the result and push it. Okay, yeah. So that's what we're doing here, is we're popping it here, we negate it, and we push it back on the stack. Lox's approach to error handling is rather spare. All errors are fatal. Oops. I just heard another follow, but I don't see the follow. Okay, I missed it. Whatever it was. Sorry. There's no way for a user to recover from an error. If Lox were a real language, this is one of the first things I would remedy. Oh, okay. Yeah. To access a value, we use a new little function, peek. Yep, that's what we're doing here with stack, self-stack last unwrap. I wonder if it would make sense to try to just say self-peek, and it would automatically do that, and self-pop would do this, so we wouldn't have to do all these things here. Which would, make the code a little cleaner. So yeah, why not? Why don't we do that? Hopefully this will be more than useful just for this. So we'll create a pop function, which takes a not self and returns a value. And all we're going to say is self stack pop. And then we can change all our self stack pops with self pop. And that still works. Okay, and then so it makes the code a little cleaner, and then we can create a peek. we can actually create like an is number, right? Oh, we have peak distance. Interesting. So why don't we do that, since that apparently is a thing. So we'll say self stack, open bracket, -1 minus distance. All right. We don't have to do that, right? It's just a vec. Yeah. Trait neg is not available for view size. So right. So we have to fiddle around with this. Distance is going to be, oh, I see, -1. Oh, okay. So this is the stack top. So we want distance to be self stack len minus distance -1. Right, because if len is 3, then we want to say 3 minus 0. To get the top one, we want to look at 2, right? So it's going to be 3 minus 0 minus 1, which is 2. Okay. And then we want to say self stack peak, which doesn't exist anymore. Oh, self stack last. Right, that's what we changed. So we're going to call this peak 0. There, okay. So that's good. So now we're kind of implementing their lock stuff a little more in this vein. You've certain called variadic functions, ones that take a varying number of arguments. Yeah, so what I'm doing is I'm cheating and using format, or I will be using format once it's needed. And our error function is just going to take a two-stringable. So this is the way variadic functions work in C. You put ... on in the function signature, and then just say start with the named value just before the ... and then vf printf. There's a whole bunch of variadic print vs and printf and all that kind of stuff. To convert it from this into a string in some form or another. And this, all I'm doing here is just printing out what we're given, and I'm allowing the caller of runtime error to just call format to generate it, which seems to be the way to go with Rust, I guess. All right. After we show the hopefully helpful error message, we tell the user which line of their code was being executed when the error occurred. Just showing the immediate line where the error occurred doesn't provide much context. Better would be to a full stack trace, but we don't even have functions to call yet, so there's no call stack to trace. For a compiler to do this job right, that corresponds to the line of source code that the bytecode was compiled from. We look into the chunks debug line array using the current bytecode instruction index -1. That's because the interpreter advances past each instruction before executing it. So at the point we call runtime error, the failed instruction is the previous one. Right, so we got the -1 right there. That's VA list. We have to include standard args. Okay, now the binary arithmetic operator. So we have to check each one of these in binary op. So this, I think, is where we go here in binary op. We want to make sure that A and B are both number values. And we have this function here is number. And maybe we should add that. We can add that to value, right? Somewhere in here we implement this. So say pubfun is value. Oh, is number. Self. Bool. If, oh, I was going to say if let value number equals self, true, else false. But then I hesitated because typically when you don't want to do an if binary condition and then return it. You just want to return the binary, but you can't do it any other way, I don't think. I mean, I could use a match, but I think this is simpler. Except I forgot the closing brace here. What do I need to do? We still haven't done reset stack. Oh, apparently there was a reset stack in a previous, okay. And I just ignored it or skipped over it or missed it or something. There's no reset stack there. There's no reset stack there. Oh, there it is. Oh, okay. Okay, so let's just write a quick reset stack here. And all we're going to say is stack, self, stack, clear. Right? Okay, so now all we have left is this value error, which is this expression has ampersand value array, and this is this. So I think can we do this? Nope. Oh, I'm in value array, that's why. We want to put it in value. Do we have equal value? We do not. Okay. All right, now we have 4 warnings. Right, because we're not using isNumber. So in source VM, we can check in binary op. Right, we want to check to see if A and B are numbers. So let's go back to this thing here. Right here. All right, so we want to check to make sure that A and B are numbers. If not A is number, or not B. Oh, we want to do it before we pop. I see. So if not, and we're going to use the peak. Self peak 0 is number, or not self peak 1 is number. And we're going to return a runtime error, self runtime. I guess it doesn't matter if we pop them, because we're going to reset the stack as soon as we call runtime error, right? And this is just operands must be numbered. Oh, we have to pass in the chunk. Oh, damn, we don't have the chunk. Yeah, and if I add the chunk here, it's going to make everybody unhappy, isn't it? Right? Chunk none. And instead of saying self-run chunk, I say self.chunk plus some chunk. And that's not going to work, right? If let some chunk equals self-chunk. That's bad. That's very bad. Oh, and then everything blows up because I forgot to close a delimiter somewhere along the way. Where? Oh, in the middle of our binary op thing. Okay, let's ignore this for now. Oh, expected. I guess we can do that. And it has to be mutable. Oh, we don't need the chunk to be mutable, right? It doesn't matter if it's mutable or not. What's it complaining about here? Oh. This is returning. Okay, returning. Okay, so this should be returning error. And this should just be panicking. Error chunk. Be fine. What's wrong with this? Oh, chunk 3. But we've already put it in there. I guess we call self chunk 3. And then self chunk equals none. Still doesn't like that. Oh, no. No, still doesn't like it because the move occurs because blah blah blah. Let's start borrowing. We don't actually need to do this free business. I'm gonna blow that away and then just say self chunk equals none, and it'll just drop the chunk at that point. Right? Oh, and now we have borrow checker problems, right? Mutable borrow occurs here. Oh, can I just say this? Like this? No, like this? Nope. All right, so all of this is bad. So the question is, the reason I'm doing all this mess, let's undo until we get this back, is because I want access to the chunk right? Okay, yeah, now we're here. I want to be able to access the chunk here to generate the runtime error. But because the chunk is not in the VM, it's just sort of hanging out on the side here in our interpret function. We can't, we don't have access to it in the binary op. The only other way to do it would be to pass the chunk down again. So I was saying, okay, well, let's fix it up so we don't have to pass the chunk everywhere. Here we're passing chunk in, and we're passing chunk into read byte, and we're passing it into read constant, and now we're going to have to pass it into these binary ops. And so it's just getting more and more painful. So there should be a way that I can specify to say, okay, here's some source. The source gets converted to a chunk. I should be able to convert this chunk and then give it to the VM to use. Can I do it using, so I don't want to use a ref cell, right? Because if I did it using a ref cell, then I could just stick it in there and have it. I was thinking maybe chunk, we could say a reference to a chunk, like that. And then, oh, but we still need it to be optionable. Right, so I'd have to say chunk new. Right, and then replace it here. Oops. And then this needs a tick A, which means main is going to need tick A. Ooh. Oh, so that's temporary based here. It's still a temporary value. And that doesn't help. You still need the lifetime thing there. Okay. So what's I mean, this would be the other way to do it. Still using that option. So if we do this and then we do this, right? So this compiles. Compiler new. So now we have the chunk here, and we should be able to say self chunk equals, because we're mutable, is equal to some chunk, right? I can do that. I can't do that. Oh, I can't do that. Chunk doesn't live long enough. Oh, because we're creating it here, and then I can't. If I say self chunk equals none, the compiler's not going to be smart enough to see that we're dropping it. Yeah. Card chunk is borrowed for A for the entire lifetime of the So then, what do we do? Use standard, make it an RC. That way we can reference count it. Like that, and then we can just say some chunk, or maybe we can make it like this, RC new. Hi Epic, how are you? Epic says, was just about to ask if you're still doing this to learn Rust or if it's about interpreter crafting. Then you run into borrow checker problem, thus answering my question. Yeah, I'm still learning Rust. This is all about learning Rust. RC new, none. And now this is no longer, chunk is, oh yeah, we can't do it this way, right? Because this has to still be a chunk, but then we have to say RC new here. Some chunk. That's some chunk, I'll say. Okay. And then RC new none. And now we have a lifetime problem again. So even though, so flip it around, right? Option RC. Oops. Chunk. Right, and then we can say RC new. Chunk new. And then this will be some RC clone chunk. And this becomes none. And this becomes none. Nope. Oh, I forgot a semicolon. Nope. Expected chunk found chunk. Expected ampersand chunk found struct chunk. Oh, yeah, I can just clone the RC, right? Wait a minute. I thought I could clone. Okay, it was expecting an RC to a reference to a chunk. Isn't that what you need? Don't you need a reference? You can't do this, right? Cannot borrow as mutable. Help trait deref mute is required to modify through dereference, but it's not implemented for this. I want to be able to pass in the chunk, and okay, so can I do, I have to create the chunk inside the RC. The compiler needs a mutable reference to a chunk. I can make this an RC, right? Looks like I'm already using riff cells. And now this doesn't work. Yeah, okay. Expecting a RC to a mutable chunk, but found a mutable RC to a chunk. Okay. Can I do this? Okay, so how do I make this mutable? You can't just throw a mutt in there. Can I do this? This? Because now it's going to say the reference doesn't last long enough, right? Expected? So it's expecting RC ampersand chunk, found chunk, found struct RC chunk. If I put ampersand here, now it's expecting it without the ampersand, and it found it with the ampersand. What? Oh, down here. Okay. So this is where we can put this back in. Right? And you can't bar this as mutable now. Oh, dang it. And then we still have this issue here where we're creating a temporary value. Oh my God. Okay. And all I want to do is have access to the chunk down here in binary ops, so we can call runtime error. And I want the chunk to be part of, or being able to be associated with the VM, or being able to be accessed via the VM. And I think it's reasonable to have a reference counted reference to a chunk. The question is, how do you create that without creating this? So if I do it this way, right? This is the ideal way to do it. Expected ampersand chunk found struct chunk. And if I do this, and then it'll say, right, expected ampersand chunk found a reference to an RC. So can we do that in new here? Can we change this to an ampersand chunk? Oh, and now this needs an explicit lifetime parameter. Oh, lifetime is A is already there. Can I just use it then? Okay, so now we're down here where we expected a reference to a chunk, and we got instead a chunk. Okay, so can I do this? Right, now we don't need a lifetime. And now we have this problem. because we can't borrow this as mutable. So this is our compiler, right? So we have this compiler here. What we can do is clone the RC, right? So instead of doing it this way, we can make this an RC of does it need to be mutable? Yeah, because we need to be able to insert stuff onto the chunk. So we need to make this a mutable. Can we do it this way? Oops. Because we're passing in a mutable chunk. Can we do that here? Can we say chunk.clone? It's saying consider mutably borrowing here, but it won't allow me to do it that way. Oh, and then we have other error where we can't write the byte and we can't add a constant because we can't borrow it as mutable. Although we have this mutable here. Cannot borrow data in RC as mutable, but we should be able to. All I want to do at that line on 131 is clone the chunk, and I can't do that, right? Because expected a mutable reference and found a struct. Can I do that? Cannot return value referencing the temporary value. So we're getting this clone right here of the RC. Boy. Epic says, are you looking to change the outer RC or the inner value? I'm trying to change chunk. Chunk needs to be mutable. And I thought by having a mutable, oh, this is a mutable reference to the RC. Yeah, and the problem is if I do this, it's going to mess up what I'm passing in. Yeah, so I want to be able to clone the RC, but have a mutable reference to it. So I can modify it as I'm running the compiler. So is this all? Oh no, I did a bunch of changes here. I should have saved what I was in the middle of, because now everything's messed up, right? All right, let's switch back to what did I have in the compiler? I'm going to undo a bunch of these changes here. Okay, so I'm just going to make this a chunk. Epic says, note that if you want to modify the shared data, RC is paired with ref cell. Right, yeah, I mean, that's the way to do it, right? So let's do this with here, and then compiler still has this. Oh. And this becomes chunk, and then this becomes just mute chunk, right? Without the RC. Oops, I left that in there. Oops, okay, so we're really messed up here. Let's get rid of chunk from here. Let's go back to using chunk, passing the chunk in without the RC. I just want to get it back to the state it was in before. We don't do that anymore. We don't do that anymore. And we don't have that. And then this is messed up. So what was it before? It's chunk, there's compiler. Oh, I left the mut out, okay. What else is messed up? This has got to be mute chunk. So I put the mute in the wrong spot here. Like this. I'm just trying to get back to where we were before. I should have saved what I was doing. There's value. Okay, so that's all right. Chunk free. I'm just going to complain about that. And there's that. Okay. And why doesn't it like this? Types different immutability. Oh, do I have to pass a lot here? No? Yes. Okay. So, okay. Now we're back to kind of where we were before. We do have 8 errors. Oh, because now we have all these RCs. In compiler and VM. And we're not calling isNumber yet. Okay. And then isNumber. Yeah, and then we can actually add isNumber here. And we can say if not self peak 0 is number. Then we'll do the runtime error. Otherwise, we'll do this. Right. Okay. Now we're down to 5. Okay. And those 5 are free is not used, right? Because I took out the call to free. Oh, in VM. Chunk.free. Yeah, okay. So now it's just these 2. Okay, very good. All right. Zeta numbers. Hey, how are you? Right. So what Epic is suggesting here is changing the oh, I'm way over time. Dang it. I didn't realize what time it was. I gotta go. But changing this to be yeah, the thing is that this needs to reference the chunk that we're creating in the VM, right? So we're creating a chunk here in the VM. We're creating a compiler that saves a reference to that chunk mutably, and then we're going to modify that in the compiler here. And then we're going to use that here, that modified version. So we could do RC, right, ref cell. I'm not going to do this right now, a chunk. But then the chunk that we're modifying inside here, oh, if we created a reference to it here and then pass in that reference and then use it through the reference, then it should be the same one. All right, so let's do that tomorrow. Meanwhile, I think we're back up and running, right? Yeah. Okay. So I'm going to commit these changes. Whatever they are. Oh, adding number checking and pushing and popping. And then we need to handle this stuff here. Git commit -m. Value checking and error handling. And then what we'll do is we'll use the ref cell and our RC and stuff like that tomorrow. Zeta number says, what's free function? What does it look like, you mean? All it does is reset the stack. It's not really strictly necessary. The only reason I have it in here is because it's in the C version, and I'm calling chunk free here. I mean, chunk is going to get dropped anyway, so everything gets set anyway. So, okay. Git push. It's up there. Oh, by the way, thank you, Zeta Numbers. I got your PR, and I merged it in, and we're using it. So, yes, sorry. Again, I got to go. I'm way over time. And I will see you tomorrow where we try to use RCs and rough cells to fix my problem. Whew. All right. Take care, everyone. And I will see you tomorrow.